This video is about Descartes' Rule of Signs. Before we talk about that rule, let's review the complex conjugates theorem, which says that when you get a complex answer, or an answer that includes a real and an imaginary part, it always comes with a positive and a negative version. So complex numbers always travel in pairs. For example, 2 plus or minus 3i, or plus or minus 5i, plus or minus I. Anytime you have I in your answer, there's always a plus or minus in front of it. So imaginary answers are always going to travel in plus-minus pairs. Which means when you're looking at a function like this, you know that the degree is 5, the highest exponent is 5, and therefore there are 5 x-intercepts, or 5 solutions. However, not all of them are necessarily real. So we're going to look at a little table that shows the breakdown of the possibilities for real and imaginary solutions. There could be 5 real answers and no imaginary answers. There could be 3 real answers and 2 imaginary answers. And notice I skipped over 4 and 1. It's impossible for there only to be 1 imaginary answer because imaginary numbers always travel in plus-minus pairs. So there has to be an even number of imaginary answers, if there are any at all. And then the last possibility is that there's 1 real answer and 4 imaginary answers. And those are the possible solutions for this x to the 5th power polynomial. Now, Descartes' Rule of Signs, which we're going to look at on the next slide, dives into just the real category, okay, just the real answers. And he looks even more closely at the real answers and tries to figure out if he can determine how many are positive and how many are negative, just within the real answers. So Descartes' Rule of Signs is a way of determining how many of the real zeros might be positive or negative. So it's another thing that you can use to analyze a polynomial function. Before you've graphed it, before you've solved it, you can use this rule to figure out how many of the real zeros might be positive or negative. How does he do it? So to figure out the possible positive answers, you want to count the sign changes in the function f of x. So sign changes meaning when does the coefficient of the term change from being positive to negative, and negative back to positive, and so on. And we'll look at an example in a minute. To figure out the number of possible negative real solutions, you'd count the sign changes in f of negative x. So the same function with all of the x values changed to negative x, simplify it and then count those sign changes, and that'll help you figure out how many might be negative. So let's look at an example of how this is done. Determine the possible numbers of positive real zeros, negative real zeros, and imaginary zeros for this function. So the function is x to the 6th power. We know there are 6 solutions altogether, but some might be imaginary and some might be real. And within the real category, some might be positive, some might be negative. So first let's figure out the number of possible positive real zeros. So remember, to do this, we're going to count the sign changes in the function f of x. So here's the function. The sign changes any time that the coefficient goes from being positive to negative or negative to positive. So I see that it starts out as positive x to the 6th power and immediately changes to negative 2, x to the 5th power. So there's one sign change. Positive then changes back, or negative then changes back to positive, so there's a second sign change. Positive then changes back to negative, there's a third. And then it stays negative for the rest of the function. So I'm counting 1, 2, 3 sign changes, which means that the possible positive real solutions, there might either be 3 of them, or anything less than that, counting by 2s, all the way until we get down to 0, right? Because we don't go to negative numbers for possible numbers of solutions. So we would say that there are either 3 or 1 possible positive real zeros to this function. So 3 because we counted 3 sign changes and then decreased that by 2. If we had gotten 5 sign changes, our answer would be 5 or 3 or 1. Right? We're always going to be decreasing by 2s. To figure out the possible negative real zeros, we're going to count the sign changes in f of negative x, which means we need to replace all of the x's in this function with negative x. So it looks pretty long and complicated at first because I'm showing out the work. If you skip this step where you show the work, that's fine, because eventually we will have to simplify this. So I've replaced x with negative x in parentheses everywhere that I see it. It is very important that you use parentheses when replacing these x's, because the negatives are greatly affected by whether the exponent is an even number or an odd number, like 6th power or 5th power or 4th power. So let's look at why. When we go to simplify this, the first term right here is negative x to the 6th power. because negative x is in parentheses, it's a negative times a negative, a negative times a negative, a negative times a negative again. So 6 times, and it ends up being positive x to the 6th power. So my first term is positive x to the 6th power. When I simplify this, negative x to the 5th power, it would stay negative, but there was already a negative 2 in front of it here, and so it simplifies to positive 2x to the 5th power, and so on. I have to go through each term and simplify. This term comes out positive. This term would come out negative, but then there was a negative and 10 in front of it, so it's positive. Finally, we get a term where the exponent makes it come out positive, but there was a negative 6 in front of it. So we have negative 6 x to the 2nd power. Excuse me, this should say to the 3rd power here. This should say to the 2nd power. So we have negative 6 x to the 2nd power. We have plus 8x, and we have minus 8. So in my simplified function here, now I'm going to count the sign changes. Positive, stays positive, stays positive, stays positive. It doesn't change signs until here, a positive becoming a negative. Then negative becomes positive, positive becomes negative. So again, there are 3 sign changes, so maximum number of negatives we could have is 3 negative zeros. And it could also be 1, because we're going to decrease that number by 2 as well. So it could be 3 or 1. So then we know with 6 zeros altogether, it's asking us to figure out, if we go back up to the original question, how many are possible positive real zeros, negative real zeros, and imaginary zeros. We're going to look at all of our possible combinations here. So we've got, let's extend the page, give ourselves a little bit of room. We're looking at positive and real. We're looking at negative and real. And we're looking at imaginary solutions, okay? So we determined that there could be 3 positive real answers. And let's say there are 3 real negative answers as well. So we're taking the most of the positive and the most of the negative, which would mean there would be no room left for imaginary answers because there can only be 6 altogether. It was also possible to have 3 positive reals and only 1 negative real, right? Because here we had 3 or 1 as our possibilities for negatives. So if there were 3 positive real and 1 negative real, that would leave room for 2 imaginary solutions. There could be 1 positive real and 3 negative real, which would leave room for 2 of these. There could be 1 positive real and 1 negative real, so the low end of both of those, in which case there would be room for 4 imaginary solutions. And those are all the possibilities for the solutions to the original function f of x. And that is all.